A static electric field is produced by charges that stay in one place and do not move. This field causes force on other charges nearby. The strength and direction of this force are described by Coulomb's law, while electric field intensity E shows how strong the field is at a point where charges are spread out like along a line over a space or inside a volume. We calculate the total field using the idea of continuous charges distributions. Lastly, electric flux density tells us how much electric field passes through an area, especially in materials.
On this slide, we see the basic statement of Coulomb's law. Coulomb's law defines the electrostatic force between 2 point charges. The force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Here, Q1 and Q2 are the charges in coulombs, R in the distance in meter, and F is the force in newtons. This simple law helps us calculate the exact force acting between any 2 point charges. This slide shows the vector form of Coulomb's law. In a real situation, force is not just a number, it also has a direction. The vector form allows us to find both the magnitude and the exact direction of the force. It explains that like charges repel each other while opposite charges attract. The sign of the product Q1 and Q2 tells us if the force pulls or pushes the charges. To apply Coulomb's law correctly, we must meet certain conditions. First, the charges must act like a point charges, meaning their physical size is very small compared to the distance between them. Second, the charges must be stationary, they should not be moving. Thirdly, we always consider if the sign Q1 and Q2 is positive, the force is repulsive. If it is negative, the force is attractive. This condition ensures that the calculation remain accurate. Finally, Coulomb's law leads us to the concept of electric field intensity, denoted as E. The electric field intensity is simply the force per unit test charge placed in the field. It tells us both how strong in the field and it is which direction it will push the charges. Understanding E helps us describe the effect of a charge on the space around it, and it connects directly to the force calculation using Coulomb's law.
Electric field intensity, which is E. Electric field intensity is the force per unit test charges placed in the electric field. It shows how strong and in what direction a charge will be pushed if placed in that field. Electric field intensity. Thus, the electric field E is defined as the limit of the force F divided by a test charge, which is Q, as the test charge approaches 0. Or you can say E is equal to F over Q. In general, for a point charge Q creating an electric field at a point, the electric field E is equal to Q divided by 4 pi epsilon naught R square multiplied by the unit vector A sub R. Or you can say the electric field E is equal to Q times the vector quantity of R minus R prime divided by 4 epsilon naught R minus R prime cubed. For n charge system, the electric field is equal to 1 over 4 pi epsilon naught multiplied by the sum from the k equals to n of Q sub k times the vector quantity of R minus R sub k divided by magnitude of R minus R sub k cubed. Next, property of electric field and field line. Remember this key point. First, more field lines is equal to stronger field. Second, stronger field is equal to stronger push on a charge. Third, arrow shows where a positive charge moves. 4. Line go out from positive into negative charges. 5. Field line never cross. 6. A charge in a field feels like a push. 7. The push depends on if the charge is positive or negative. Then you can see the electric field of opposite charge, which is opposite charges brought toward each other experience an attractive force. As you can see, the field line originates from the positively charged particle and at the negative charged particle. Near each particle, the field lines are denser, indicating a stronger electric field close to the charge. Like charges. Like charges brought towards each other experience a repulsive force. For positive charges, electric field lines radiate outwards in all directions. As you can see, the field lines repel each other.
And now, we will discuss about electric fields due to point and continuous charge distribution for lines, surface, and volume charge densities. In this topic, we want to find the electric field caused by different types of charge distribution. There is three. First is line of charge, second, surface charge, and third, volume charge. For your information, there are four types of equation that we need to know. First is charge element, second, electric field due to the charge element, third is electric field at point P, and fourth is special case, infinite line. Before we continue to discuss all of the equation, let's take a look at these key terms first. It is very important so that we can solve all of the equation. Next, I want to highlight only important key points on each equation. Okay, let's discuss about the linear charge equation. For charge element, the key point is rho L and dl. For electric field due to the charge element, the key point is Coulomb constant K, R, and A hat R. A hat R refer to direction from the charge piece to the point. For electric field at point P, we add up all the small fields from each dl piece along the wire. For special case or infinite line, the key point is R and A hat R. A hat R refer to direction away from the wire. This special case is a shortcut if the wire is infinitely long. Next, we will discuss about surface charge equation. For charge element, the key point is rho S and ds. There is no key point for electric field due to the charge element. For electric field at point P, there is also no key point, and for special case or infinite line, the key point is A hat n, which refer to perpendicular direction from the surface. And lastly, we will discuss about volume charge equation. For charge element, the key point is rho V and dV. For electric field due to the charge element, there is no key point. For electric field at point P, there is also no key point, and for special case, there is no formula. It is because it very complex in practice.
Electric flux density, represented by D, tells us how much electric field passes through a surface. It's measured in coulombs per square meter and is crucial for understanding field strength and material behavior. Okay, next we have D due to point charge. First, we have electric flux density due to point charge, where this means that the flux densities spread out from a point charge equally in all directions. The direction is given by the unit vector AR, which points radially away from the charge. In summary, a static electric field describes the invisible force field created by stationary charges. It's the starting point for understanding more advanced topics like electric flux density, capacitance, and electromagnetic wave. Mastering this topic gives us the foundation to explore how chargers interact in both nature and technology.